This video is on getting maximum power to an impedance load, but before we talk about how to do that, I just wanted to review what we previously discussed in DC circuits with the condition of getting max power to a resistive load. So remember, we utilized a Thevenin equivalent circuit, and we attached a load, and we did a derivation, mainly finding the voltage across the resistive load and then using power equal to V squared over R to come up with this expression for PRL. And then we used some calculus where we took the derivative of this function with respect to RL and then set it equal to 0. And then we looked at what value of RL would make this whole thing equal to 0. And the result, the important result, was right here, that when the load resistance is equal to the Thevenin resistance, that's when you get maximum power absorbed by the load resistance. So this video we're interested in, well, what if we had impedances? When would we get maximum power to an impedance load? And one of the things that comes up is complex conjugate. So this is just a quick review of some complex math where if you have A plus or minus JB as your complex number, and then what this asterisk means is that you're taking the complex conjugate of what's inside the parentheses. Well, if you have A plus JB, the complex conjugate would just be A minus JB, and if you have A minus JB, complex conjugate would be A plus JB. So complex conjugate in rectangular form, the real parts are the same, the imaginary parts have opposite sign, and the magnitude of the imaginary parts are the same. Excuse me. In polar form, when you take the complex conjugate, all it does is affect the sign. Same magnitude because these numbers don't change, but opposite sign since the sign changes for the imaginary part. Okay, so that's just some review information that will be handy for our derivation of when we get maximum power to an impedance load. So just like the DC case, we have a Thevenin equivalent at 2 nodes here, but since it's an AC circuit, we have impedance instead of resistance, and then we hook up an impedance load. And you know from previous discussion that power triangle is a convenient way to find out what you need to find out about power in an AC circuit. So here we're using L for load, and just like we talked about, the real part is your P average, your absorbed power. The imaginary here is your reactive power. So again, this is Q load, not inductor. Okay, L stands for load here, not inductance. And then your total power, what we think of as the total power, complex power. Well, the magnitude is just this hypotenuse of this right triangle. So the first thing when you're trying to determine max power to an impedance load, okay, so that's a W there. Sorry, well, let's clean that up. Okay, so try that again. Right. So max power to an impedance load. The first thing you need to determine is, well, what power are you talking about? Because in an AC circuit, we have all these different powers absorbed, exchanged, and what we think of as the total, the complex power, or apparent power when it's the magnitude. So it should make sense that we want to maximize the absorbed power, because as we stated in a earlier lecture, the absorbed power, that represents the amount of power that's that can possibly be converted. The amount of electrical power that can possibly be converted, say, to mechanical power by a motor. So that's what we want to maximize. And I wrote here that that maximum or that average power is equal to the real part of the apparent power, okay, of your complex power, right? Because it's the adjacent side of this right triangle. And we also know from previous discussion that complex power is just voltage times complex conjugate of current. So what we're going to do is come up with expressions for VL and IL that are in terms of these impedances, and then we'll continue on to see what the answer to this question is. What value does ZL have to be to get maximum power to ZL? So first of all, VL from voltage divider equation would just be VS times a ratio where we have ZL in the numerator and ZS plus ZL in the denominator. Okay, so that's our IL, or excuse me, VL. And then IL, we can just write as VS divided by ZS plus ZL. ZL. And then complex conjugate would just be that we take the complex conjugate of both the numerator and denominator. Okay, so now we can take this VL, substitute here, and take this IL complex conjugate, substitute here. And if we do a bunch of algebraic manipulation, which I have on this handout here, okay, see here's VL and IL complex conjugate substituted in. So if we just follow through here, and you can go through this on your own, but the important result here is at the bottom of the page where we have that you can write that power P average for the load. Okay, so if we go back to our workbook here, we'll go over to the next page. So we can write that PL, which is P average of the load, is equal to the following. It's equal to, we got VS, and again this tilde means RMS value, so we're using RMS value here for the V. Okay, but we got that, and then in the denominator we have RS plus RL squared plus the reactances squared. So let me just double check here and make sure I got the same. Yeah, so VS squared RL in the denominator, RS plus RL squared plus XS plus XL squared. So that's our expression for the average power for the load in terms of the impedances in our circuit, where we've broken up those impedances into the real part and reactance, which, as you know, is the imaginary part of the impedance. So you see, this is the equation that we want to maximize. We want to find, well, what does XL, what does XL and RL have to equal in order to make this function here a maximum? So first, let's look at the reactances. Well, to make this equation large, I would want this term here, the reactance term, to go to 0, right? Because if that goes to 0, that's going to help this entire equation here to be a big number. So to do that, we would set XL equal to minus XS, right? Because then that term would go away, and if we made this happen, we would be left with just that PL is equal to VS squared times RL over RS plus RL squared. Okay, so now we want to find, well, what is the value of RL that will maximize this, right? We got the reactance, but since we're after an impedance, we need both reactance and resistance. Well, look, this equation that this reduces to once we make this happen, the reactances canceling. If you look back to the DC case, it's the same form of expression, see, that we got in the DC case. So just like when we took the derivative of this equation with respect to RL and then set it equal to 0, and we found RL equal to R Thevenin, well, in the AC case, once we make the reactances cancel out, it's the same form of equation, so I'm going to get that this is a maximum when RL is equal to RS. Okay, so you see, this is the condition for max power, okay, maximum P average at an impedance load. You want the resistance of the load to match the resistance of the source, and you want the reactance of the load to be the same magnitude as the reactance of the source but opposite sign. And you can summarize this by saying that you want ZL to equal the complex conjugate of ZS, right? Because if you have equal real parts and you have equal but opposite sign imaginary parts, which is what the reactance is, well then you have a complex conjugate. So this is the important result in AC circuits, that max power, which is the P average at the load, will occur when your load impedance is the complex conjugate of your source impedance.